This mini lecture is within kinematics of a particle, and specifically we're talking about motion of a projectile. So here we're going to be able to analyze the free flight motion of a projectile. Okay, so if you take a look at the diagram top left, the description is that we have this kicker, right? And a good kicker instinctively knows at what angle, we'll call the angle theta, and initial velocity v sub a, that he has to kick the ball to make this field goal in football. So for a given kick strength, the question could be, okay, at what angle should the ball be kicked to get the maximum distance, right? So this is one application of what we're doing today. The next thing is the picture to the top right. So there's a basketball that's being shot at a certain angle. So our question could be for this person, what parameters should you shoot or should you consider in order for the basketball to go through the net, right? Is it the distance, the speed, the basket location, or anything else? All right, and then in the picture at the bottom middle, the firefighter. So the firefighter, they need to know the maximum height on the wall that she can project water from the hose. Okay, so our question is, what parameters would you program into a RISC computer to find the angle, right? That angle we'll call theta. And what parameters would you program into a RISC computer to find angle theta that she should use to hold the hose? Okay, so in looking at the motion of a projectile, we'll get to this picture in a second, but we'll consider this part one and part two. So for part one, in considering the motion of a projectile motion can be treated as two rectilinear motions, right? Two rectilinear motions. One in the horizontal direction, right? Horizontal direction, experiencing zero acceleration. And the other is in the vertical direction, experiencing constant acceleration, right, from gravity. All right, so now for this illustration, we're considering the two balls on the left. The red ball falls from the rest, whereas the yellow ball is given also this horizontal velocity. So each picture in this sequence is taken after the same time interval. But notice both balls are subject to the same downward acceleration since they remain at the same elevation at every instant. Also, note that the horizontal distance between the successive photos of the yellow ball is constant since the velocity in the horizontal direction is constant. Okay, next is kinematic equations. So we said kinematic equations, horizontal motion. All right, so since a sub x equals 0, right, the velocity in the horizontal direction remains constant. Since a sub x is equal to 0, the velocity in the horizontal direction, right, this remains constant, where we have v sub x is equal to v sub, we'll call it ox And the position in the x direction can be determined by x is equal to xo plus vox t. All right, and then we formulate our questions. Going through everything, always formulate questions. Why is a sub x equal to 0, right? Think about that, and you'll figure it out. What assumption must be made if the movement is through the air? Why is a sub x equal to 0? And what assumption must be made if the movement is through the air? Okay, then there will be kinematic equations. I'll leave that one up, but kinematic equations. And this time we're looking at vertical motion. All right, so since the positive y-axis is directed upward, a sub y is equal to negative g. Since the positive y-axis is directed upward, a sub y is equal to negative g. So application of the constant acceleration equations yields vy minus voy minus gt. We have y is equal to yo plus voy t minus 1/2 gt squared, and then vy squared equals voy, that squared, minus 2g y minus yo. So for any given problem, only two of these three equations can be used. For any given problem, only two of these three equations can be used. Okay, looking into our first example, we're given v sub a and theta. They give us v sub a, 10 meters per second, and theta is 30 degrees. We're told to find the horizontal distance it travels and v sub c, right? Let's find the horizontal distance that this object travels and v sub c. So what's our plan? Our plan is to apply the kinematic relations in x and y directions. Apply the kinematic relations in x and y directions. All right, so using v sub ax equals 10 cosine 30, right? And v sub ay equals 10 sine 30. We can write v sub x equals 10 cosine 30, v sub y equals 10 sine 30, and then we'll have to subtract 9.81 times t. Okay, so now x is equal to 10 cosine 30 t, y is equal to 10 sine 30 t minus 1/2 9.81 t squared. Okay, so since you can say since y equals 0 at that point C, you look back at the diagram, y is equal to 0 at point C, then 0 is equal to 10 sine 30 t minus 1/2 9.81 t squared, and for us that yields t being equal to 0 and 1.019 seconds. Okay, so given a quadratic, you're always given two solutions, right? But only the time of 1.019 seconds makes sense. So velocity components at c. Velocity components at c. Let's see what they are. All right, so we have V of Cx equals 10 cosine 30. Okay, so that's going to give us 8.66 meters per second in that horizontal direction. VCy is 10 sine 30, all right, minus the 9.81 times 1.019 that we just found, that t value we found not too long ago, and that's going to get us negative 5 meters per second, or we could just say 5 meters per second in that vertical direction. Okay, so then we have VC is equal to, we take the square root of 8.66 squared plus negative 5 squared, and we'll get 10 meters per second. So the horizontal distance the ball travels, is x is equal to 10 cosine 30 times t. Again, t is 1.019, so we input that, and then we'll get 8.83 meters.